China just cut off ASML and TSMC for good. On April 12, 2025, Beijing formally terminated all procurement contracts for ASML's lithography systems and TSMC-based chip orders across state-linked firms, signaling what analysts at Bernstein called the most decisive pivot in semiconductor sovereignty since 1987. The move followed a year-long buildup of localized fabs, with China's SMIC ramping DUV-based production capacity to over 300,000 wafers per month, double its 2023 levels, according to IC Insights. For ASML, whose EUV systems account for nearly 70% of gross margin, the implications are immediate. UBS analysts report a 12% drop in advanced tool bookings from Asia in Q1 2025. TSMC, meanwhile, faces a strategic dilemma. Its $100 billion U.S. expansion, once hailed by Washington as a national security win, has now become a geopolitical constraint, as Beijing blacklists its nodes above 7 nanometers. Yet the real shock isn't China's withdrawal. It's the fact that they appear ready. And what they've built instead could make Western sanctions look like outdated scaffolding on a tower that no longer needs it. When Washington imposed sweeping restrictions on Huawei in 2020, cutting access to TSMC's advanced nodes and ASML's EUV lithography, it triggered what Credit Suisse later called the most expensive forced innovation cycle in modern tech. Within 5 years, Huawei and SMIC responded with a Mate 70 Pro, powered by a domestically manufactured 7 nanometers chip, fabricated using deep ultraviolet lithography, DUV, and self-aligned quadruple patterning, SAQP. No foreign tools. No imported wafers. The chip, analyzed by Tech Insights in February 2025, showed a transistor density 17% below Apple's A17 Pro, but was functionally competitive in AI inference benchmarks. Then came the Ascend 910C, built to rival NVIDIA's H100, and entered volume production in March 2025 at Huawei's Qingpu facility. Bloomberg confirms that over 30 domestic AI firms signed supply agreements in Q2 alone. This wasn't a workaround. It was an architectural inversion. And if China's next move succeeds, it may no longer be playing catch-up. It may be changing the direction of the race itself. SMIC's quiet bid to reach 3 nanometers without access to EUV has triggered a fracture in expert consensus. On one side, TrendForce analysts argue that without EUV, the multi-patterning complexity required for 3 nanometers nodes makes commercial yield rates virtually unachievable. On the other, teardown data from a prototype SMIC wafer, leaked in April 2025, shows a reported critical dimension shrinkage to 34 nanometers gates, bordering on 3 nanometers territory when using quadruple patterning. The cost, production time nearly triples, and reported wafer yields hover around 40%, according to IC Lab Asia. But Beijing isn't aiming for Western efficiency benchmarks. It's targeting volume and resilience, with state subsidies offsetting fabrication losses and demand guaranteed by domestic AI and defense projects. SMIC's strategy may not be economic in capitalist terms, but geopolitically, it's precise. Morgan Stanley's March report warns, China no longer needs to match TSMC's cost structure. It only needs to scale a minimally viable alternative faster than we can sanction it. NVIDIA's exit from the Chinese AI market in late 2024, driven by U.S. bans on its H100, H20, and B200 chips, created a $7+ billion vacuum, according to Reuters. Huawei didn't hesitate. In May 2025, it began mass shipments of the Ascend 910C, a chip engineered by fusing 2 910B dies in a 2.5D package to rival NVIDIA's Tensor performance. While not a monolithic 5 nanometers breakthrough, the architecture achieved 75% of H100's performance at roughly 55% of the cost. As noted by China AI Tech Watch, Huawei sold out its initial batch to state-backed cloud firms within 11 days. More significantly, SMIC's production line, using DUV lithography and adjusted AQP, achieved a 56% yield rate by mid-May, up from 31% in January. This isn't technical parity. It's strategic asymmetry. Huawei doesn't need to match NVIDIA on every metric. It only needs to supply chips that are good enough and on time. The AI war just found a new frontline. And it isn't in Silicon Valley. By Q2 2025, more than 82% of components used in China's sub-10 nm chip production were domestically sourced, according to the China Semiconductor Industry Association. SMIC's new mega fab in Shenzhen, completed in just 16 months, now produces 45 nm, 7 nm class wafers every month. Meanwhile, Shanghai Microelectronics Equipment, SME, hit its first production run of 28 nm capable steppers in March and is targeting 14 nanometers by late 2026. On the personnel front, over 1,500 engineers from TSMC and UMC have reportedly accepted multi-year contracts in mainland firms since 2022, lured by compensation packages averaging 2.3 times their previous salaries. According to Nikkei Asia, Beijing's $47 billion chip fund, restructured in 2024 under SASAC oversight, has prioritized vertical integration over global interdependence. Unlike ASML, which relies heavily on Carl Zeiss optics and German photonics for key modules, China's semiconductor ecosystem is converging, slowly but methodically. If this trend continues, the biggest threat to Western chip dominance won't be espionage or IP leakage. It will be irrelevance through redundancy. In February 2025, a leaked engineering document from China's State Key Laboratory of Laser Technology stunned analysts. A prototype blueprint for an LDP, laser-induced discharge plasma, EUV source, claiming a 90% reduction in power consumption compared to ASML's current LPP, laser-produced plasma systems. According to the Journal of Photonics, this new design replaces ASML's twin laser tin droplet system, which converts less than 0.1% of input energy into usable EUV, with a staged dual-input approach. A low-power ionizing laser, followed by high-current electrical discharge. Engineers at Applied Optics Beijing reported early lab results producing 13.5 nanometers EUV light at a 0.8% efficiency rate, roughly 8 times higher than current Western systems. Durability under fab-scale throughput remains unproven, but if scalable, the impact is real and immediate. This innovation could eliminate the need for ASML's 170 million euros EUV units, each of which consumes over 1 megawatt of power. A single leak shifted global investment narratives. But how close is China really to turning blueprints into machines? ASML's EUV supremacy is built on a process that, ironically, burns more energy than it prints wafers. A full-capacity EUV line draws power equivalent to 1,200 average U.S. homes per month, according to the International Energy Agency. Its LPP method requires 50,000 laser pulses per second, massive heat mitigation infrastructure, and mirror arrays that degrade after just 20,000 wafers. In contrast, China's proposed LDP system bypasses tin vaporization entirely, generating stable plasma via electrical discharge, emitting EUV light with minimal thermal load. Chen Wei, a former engineer at Zeiss SMT, now consulting for Asia Lith, told Bloomberg in March, if this works at industrial scale, it would shatter the energy precision trade-off we've lived with for 15 years. ASML declined to comment, but in April, it slashed its 2025 EUV shipment forecast by 18%, citing regional procurement uncertainties. Behind the scenes, ASML has begun redesigning its next-gen source architecture. Why? Because the pressure is no longer theoretical. TSMC's 2025 Arizona fab isn't just expensive, it's exposed. With $6 billion in U.S. subsidies and national security clauses baked into joint output agreements, TSMC must now prioritize Washington's strategic directives over neutral market logic. ASML, meanwhile, is stuck between three forces: Dutch regulators, American policy pressure, and Asian customer loss. In Q1 2025, TSMC's foundry utilization dropped to 76%, down from 89% a year prior, largely due to the loss of Chinese contracts, according to TrendForce. Meanwhile, Canon's FPA 1200 NZ 2C DUV system, a non-aligned alternative, has gained market share with 27 units shipped to Southeast Asia in the last 5 months. ASML's dominance isn't broken, but its moat is evaporating. And the problem for Dutch optics and Taiwanese wafers isn't just that China left the table. It's that others are now sitting in its place. But let's be clear, building an EUV system is not the same as running one. At 30,000 wafers per month with 95% uptime, China's LDP project still faces steep technical barriers. Ultra-high reflectivity mirrors, with over 100 molybdenum silicon layers, requiring defect tolerances under 0.2 nanometers. Sub-angstrom calibration tools for mask alignment, which China's domestic metrology systems still fail to achieve, according to Tokyo Electron. Photoresist compatibility. Chinese firms like Jiwa Chemical have yet to produce UV-capable polymers that meet yield variance thresholds for high-volume manufacturing. Synchronization challenges between etching, deposition, and inspection steps remain unsolved. Still, the State Council's recent funding, $9.3 billion across 4 pilot lines, signals commitment, even if not yet readiness. As Bernstein tech strategist Lisa Chow put it, China has proof of concept. What it doesn't have is repeatability under pressure. But that can change fast. Ask anyone who thought Huawei would never make a 7 nanometers chip. So let's get real. If China cuts the cord from ASML and TSMC and builds something leaner, cheaper, and more energy efficient, what happens to the global tech stack? Think about this. Every AI server, every quantum simulation, every military targeting system of the next decade will depend on who owns the light source. Right now, ASML controls that light. But what if Beijing just cracked the bulb? The blueprint was only the first fracture. The next move is already being manufactured behind closed doors. So here's the question. If China makes EUV obsolete, who rewrites the rules of war, wealth, and power? Drop your answer in the comments. Because the next move, it's already in play.